of looking to see if there's something there, you need both positive and negative alpha. So this is, every one of these dots is the output of a fit on data that's taken with real data, but with no signal injected. So I've got the real uncertainties, but no real central value. And every dot is the output of one of these bootstrap fits. So you can see that if I wanted to draw a box that enclosed these guys, or not a box, but a curve, then I'd be able to draw that. Right? So this is where these confidence intervals are going to come from. And all these points would clump if there was one signal to be found. So how do these confidence intervals get drawn? This is a non-unique problem. There's almost no, there's no unique way to draw a confidence interval. You just need to draw a box that includes 95% of your points. And then, so I had to come up with something, and I'd started doing something that I was pretty sure was right, and then Matt Turner had made a suggestion, so I now call it Turner smoothing. So what I do is I take the first, for the data I show you in a moment, it'll be 23 points coming in from the left, and I'll compute their mean and standard deviation, double it to get the 95% confidence interval, and then I'll just plot it. And then I'll drop the first one out and pick up the 24th, and I'll just scoot this window along and I'll keep recomputing. And then I don't know whether I should use the front edge or the back edge of that interval to make a plot. So I do both. The kind of magenta thing here is using the left edge, the light blue is using the right edge. And so if something's excluded by both, then it's definitely excluded. If it's included by both, it's definitely included, which is the white stuff. And if it's excluded by one, I can't tell. So I actually have a confidence interval on my confidence interval, which no one ever has, which is cool. Because then and these will just get better the more fits I make, because it reduces the discrepancy horizontally as you get more and more points. And this is a plot that actually gave me a bunch of heartburn when I was trying to put together stuff for the APS meeting. It's an injection with nothing, but it's weakly favoring one side. So it's almost 2 sigma. It just fluctuated that way when I injected simulated data, that it's starting to kind of pick up something. So that's why it's hopping across 0, which looks weird if you're used to looking at absolute value of the alpha plots. And starting to say, hey, this is kind of maybe a thing you should probably keep bootstrapping and see whether or not there's stuff there before you make a nice curve. And so the expected sensitivity I get, we'll find out what I actually get in a moment, but this is roughly what I think I'm going to get. So if I'm optimistic, I might do as well as the yellow. If I'm really conservative, I might do as well as the green, and we'll find out.
Yeah, where are yellow and green?
So yellow, it's basically this window, and then there's a few point spots right in here where the yellow sort of gets just inside the green. So you can take that whole band as your confidence band, and you'll get the same interpretation.
Or if there's a signal, then
yeah, well, if there's a signal, then
different.
Sure, but this is sensitivity. Whether there's signal or not is a separate question. Okay, so some quick mini conclusions. Let me see how I'm doing. Oh, this is great. Apologize, things are too fast. So a couple of lessons learned. I actually have a huge list of them. You can look at my book, which is coming out very soon. And there's also a computer program. You can check it out too. And the computer program writes the book, so you just get a computer program. But so measuring a force law is really hard compared to measuring one parameter. And in particular, in this plot, this is varying this is 4 orders of magnitude by going less than an order of magnitude here. So this is basically a different experiment at every length scale, and it's really hard to figure out which systematics matter where in space. It's really, really tough. So I really don't want to do that again. I'll do this experiment again, but I'd really rather measure things where I've got like one number and I can write down an error budget, and everything will be nice and simple, and I don't have to spend years making something complicated. Most short-range experiments don't have an error budget, and that includes us. That because these things are so dependent on lambda, there's not something that really tells you exactly what the biggest problem at this scale or that scale is. So you really feel like you're flying blind a lot of the time. That's the reason that I've been pushing on an experiment where I knew I had a problem with this contact potential, and I said, fine, I'm just going to do it all the way to the end and really find out where all the problems are. We also thought we could just jump in and we've got all the signal in the world in this really null geometry. We're just going to go do it, and it's going to be great. And we really should have realized that wasn't working pretty quickly, and then switched over to a campaign where we started to just delivering. Sure, it's a terrible result, but we can iterate on this thing over and over and over again and lock in on on the best result instead of really trying to get the best result out of one instrument fast. And then from a sort of social standpoint, going blind was tough because this group is really, really great at banging out fabulous results that aren't blind. And if you're, it's basically like, imagine you're like a small island nation, and the British currently rule the place, and you want to get rid of the British. And you look around at your team, and the only person on your team is Gandhi. So then, like, you can go start the Boston Tea Party and like run your big insurgency, but Gandhi's going to be like, I'm in favor of what you're doing, but I don't think that's a good idea, and I can't help you with that. So whatever I do next with this stuff, whatever we're doing, I want to be on the same team, because otherwise it's not going to be nearly as fast. So some steps forward. There's, it's easy for me to fix this contact potential voltage. It's easy for me to realign stuff. I can do that, and in time scales of less than a year, I can generate a similar result because I have all the code. I just pour everything through, run it again, and I get another result. We can switch to a new pendulum and a new attractor, and that'll get us better results, and it might also kill this battery problem. And it would be really nice to interleave the systematic tests. I don't know if you saw that. I took a bunch of science data, and then I did all my systematic stuff. And you have to believe that it's the same instrument over that time. So that's a thing that, for at least some of the systematics, I could, add a B field, turn a B field off, do the science thing, change all kinds of different parameters on the fly, and I get a faster result that I think would be even more reliable. And then, in order to resolve this interferometer sign problem, I'd love to have something that continuously injects a little offset to the interferometer tip that would let me track the sign the whole time. Okay, blind analysis. Let me hop onto my soapbox for a second. So,
Where
almost
have you been
everybody.
before?
What's up?
Where have you been up to?
Oh, so this is my only real soapbox slide, I think. Maybe not. To me, I feel like in our whole field, we all are looking for stuff beyond the standard model. More than a third of the people in the room here, but probably more than, well, actually everybody, is doing null tests. So whether you're looking for axions, you're looking for some variation in G-2, you're looking for double beta decay, you're looking for all kinds of stuff. And none of those things are immediately expected to happen. So if you measure and you perform a great experiment, you can really demonstrate that it's really sensitive and you get nothing, everybody thinks that's great. And if instead, if you got the LIBOR to unblind today and I resolve a signal at 100 sigma at 100 microns, there's a big fat signal in there, you're going to think I'm wrong. You might be right. But this is a problem because it really drives us to measure zero, because that's really safe. I can get a great job if I give you a great result right now. And I absolutely could have given you a beautiful looking result. But I want to actually find out what's really in there. So I don't have any social fixes for this, but I can technically fix some stuff. So I think you should do blind experiments, because then you don't know what you're doing. And it factors execution from interpretation, which I think is really key. And then you guys are helping with the next part, because people tend to say that, well, you did a blind experiment, that's great, but what are you going to do when you're done? And because sure, you found some problem, you're going to go fix it, everything's going to be, you'll be able to figure out what's going on. And I think that's why you should unblind stuff in public. That gives you the error bar on the experiment. It's helpful to do things in an automated way, because if there is a problem, you can just fix that one problem. I've distributed to you every way that you need to do, or everything you need to reanalyze my experiment. So then, if you're like, oh, I got this temperature thing wrong, you can fix that, and you can decide what I've got this whole measurement, you can use all of it, and then fix that one piece. And so I hope I can convince you that you can do blind null tests that are hard. And socially, we can also emphasize proper execution of an experiment. You can make a correct error budget for every systematic you know about. That is a thing that is possible. You can't guaranteed think of every systematic, but you can enumerate all the ones you know about and characterize them correctly. And we can definitely ask for that of people and proper documentation so you can figure out what they actually did. Okay, off the soapbox. What did we actually do? This blind is a terrible way to blind an experiment. But it's the only thing that I could figure out how to do. I thought about it for years. And basically what I did is I didn't look at the data. And that's a scary thing to do, because pretty much with a torsion balance, your best indicator of whether or not the balance is healthy is to look at the data. And so I actually went back and looked at my logbooks over the last week or so, And I actually knew more than I thought I did the whole time I've been analyzing. I did actually spend some time looking at data and doing a little bit of data analysis, but I didn't have my like fully tuned up data analysis software. While I was writing the code that does the blinding and unblinding, I had a bug that showed me the real data for a little while. And I kept like, I'm injecting stuff and nothing's changing, what's going on? And so at that time, I can tell you what I saw. I saw that there was a signal at 20 or 30 microns with alpha of like 100, but I don't know the sign, which is great. That made me feel a lot better because it, all these different possibilities could do different stuff. And that happened in June of 2013, and I've done a bunch of systematic corrections since then. And you'll notice that this talk is totally different from me selling you on how great my measure is. I'm telling you where all the problems are. Right? And that's something that I think being blind really makes you do, because you're like, if there's a signal in here, I want you to know which parts are right and which ones aren't. And so at the APS meeting, Dave Newell asked me, so when you see you open up the box, what are you going to do? And that discussion led to the idea that, like, I think every blind experiment should write down before they unblind what they think and what it's going to mean. And so I've got this set of concerns that are also written in my thesis. You can go check that they have the same data hash and everything. So there's this interferometer sign discrepancy. Eric had also suggested that there could be a problem that if the pendulum foil contact potential varies as a function of attractor position, that could be a thing. And it's definitely possible to test for it, but I didn't test for it. So I have to leave that as a possible systematic concern. We did do some tests to try to verify that there were no small scale magnetic effects, but I can't guarantee that there aren't any. So it could be that you've got like ferromagnetic dust that we couldn't pick up with our sensor. It could still be in there. We acid etched everything. It should be clean. From a metrology perspective, if there is a piece of dust that I didn't know about, I did a lot of stuff to try to guarantee I had no dust. It could affect what I claim in terms of limits. It won't affect whether I see a signal or not because my experiment's null. I did a test for whether or not the light, the sub-milliwatt of power from the interferometer laser striking the foil could potentially locally heat it. I did do a test for it, but because of a record-keeping problem, I couldn't actually claim a limit on it, so I'm not going to. So if I see a thing, it could be that. I don't think so, but it could be. And then you could always met in some wonderful Casimir subtlety. Those are cool. I don't expect, it's hard to get, there's this question of how thick of a foil does a foil need to be in order for it to absolutely act like a conductor all the time for everything. And you can come up with lots of sort of hand-wavy arguments that are compelling about it, but it's hard to, there's nothing I can cite that says absolutely the Casimir force doesn't get through if it's a thickness of 10 microns. And whether or not a signal appears in this experiment or not, I think both that it's easy to upgrade this thing at least a little bit, which is going to get most of our original design sensitivity out of it. And I also think we should definitely run the wedge pendulum because it's even more sensitive. So, and we don't know which experiment might be more sensitive in the end. So whether we see something or not, I think we should do it again.
Charlie, may I ask you, but in these concerns, do you quantify them in terms of uncertainties? Or
for this, I didn't. I sort of regard this as the squishy qualitative part of the, because you can write up an error budget, but then, if you're talking with your experimentalist friends about it, you're like, oh yeah, there's that like thing. We think it's about this big, but like, and it's the last thing you do before you went blind. So you're like, oh, we didn't have time for that. I want to just.
These are the mistakes.
Right. Yeah. Yeah, because absolutely you can execute it better. Yeah, yeah. And it's amazing when you're blind. You're like, oh man, I gotta get all this stuff in there because if there's a thing, I need to tell them about it before I open up the box. Okay. And so I feel like I should also tell you what my bias is. Surely I want to find the right answer, but I also really want to see nothing. And the reason is that I want to convince everybody involved in this so I'm looking in a parameter space where mostly other people have already looked. And if I don't see nothing, I don't think I'm going to be able to convince people that this is the thing we should do. So that's sort of where I'm sitting, but definitely the experiment's designed to tell us whatever's true. How's this unblinding thing going to go? So all I did was I had been simulating my results I would compute the torque stuff all the way up until I could pick off the uncertainties per cut, and then I would inject fake data after that and do all my studies from there. And so I just flip the switch that says now we'll let real data flow through that pipeline and we'll see what happens. So this started on April 24th because these fits there's a bunch of simulated annealing and the method I have to use is slow. So it's been running for a while. It finished on, I guess, a little more than a day ago. And you can go look. There's a tweet that has the hash of the git commit from when this was the last thing that we used. And then we had to tweak a thing in order to make it actually run, so then there's a second hash. And we also had to compute the SHA-sum of the entire data, because there's no way to include a hash into a thing whose hash you later need by definition. So we had to do that. And then we monitored it daily just to make sure that it wasn't crashing, and that Matt Sternberg has looked to make sure that there's nothing totally crazy. There's no nans, there's no ifs, the systematic behavior is not stupid. And so far as I know, nobody's seen the gravity channel. So, and some past, these are defense results, which I put up because both they were here, and my experiment is only going to give you results that look like the upper half. So the fit is designed to find a thing if there's a thing to find. And so both Dan Kapner and Ted Cook resolved signals at the time of their thesis defense, and they were still able to get limits out that look like these, because while there's a signal resolved there, you can also place limits at other lengths. And whereas my thing is really designed, if there's a thing, I'm going to give it to you, and I'm not going to tell you anything else because I found a thing. So, and this result went away because we later found that there was a bent pendulum that was just a little curved, which is enough to make a signal like this. And the signal that Ted sees is way out. It scales, so that pendulum is about this big, and this is comparable to the size of the pendulum. So it's very far away. If you're, and it's much better tested by other experiments. So if there's something out there, like this wasn't what that experiment was designed to measure. But I just put these there because if I see a thing, it's because I'm gonna clump in there. I might still be able to extract some other result by some other statistical method.
And remind us where you are
On this plot? So I'm going to, if you compare with these guys, I expect to, at best, just match Dan, which is this solid curve. And I apologize that these, I guess the horizontal axes are the same. And so then I have to teach you what does it look like if I see a signal and what does it look like if I don't. So this is what it looks like if I don't. This is the same plot I showed you before. This is something where I've injected a bunch of stuff, or I've injected nothing with real uncertainties. And then when I unblind, if I show you